Awesome. All right. Well, there's already a bunch of people out there on the intertubes to witness this once in a lifetime. Maybe it'll happen again next time there's some amazing announcement, amazing discovery. But I'm joined today by Sean M. Carroll of the California Institute of Technology, which I believe is a small technical college in LA. Is that right?
It is, yeah. It's, for vocational students who want to learn a trade.
That's right. There's no better place to learn a trade, I suppose. Let me close up all these windows here. And you're reading me loud and clear, I hope?
I can hear you. You sound good.
Great. So, hopefully people out there are watching, and it is a treat to welcome none other than Sean Carroll, Professor Dr. Sean Carroll of the California Institute of Technology, who has been a great influence on me and many other scientists throughout the years. And one of the things that he is best known for outside of scientific communication, as many books, is that he is one of the originators of a modification to none other than the Maxwell's equations of electromagnetism. That I find quite intriguing, and it's something that I thought of no one better to speak to than Sean about this claimed potential evidence for possible discovery of what is known as cosmic birefringence, which would be sort of a mysterious discovery if confirmed. Let me make sure that Sean is being shown. Yes, he is. And here I am. I'm Brian Keating. You know what I look like, but it's a pleasure to bring you this live today stream. And there's a lot of people in the chat room already asking questions. I encourage you to ask questions in the chat, and we'll try to get to them. And Sean is joining us from his laboratory. When I came to visit you last time, you only had Richard Feynman's desk. How'd you get this resplendent laboratory, Sean?
You thought I was a theorist, but no. This is, I have my secret experiments. I don't want to tell anyone any of the details. The world isn't quite ready for them yet.
It's another talent that Sean has that only now are we privy to. So, Sean, I put together some slides, which people can access if they go to my website under blog. So I'll put that in the chat room right now. People can go there and get show notes. Just look for the Sean Carroll episode. That is listed there. I run a website which features links to many interviews, including ones like this, which you can find. I'll put this also in the chat room on the actual internet, on the actual YouTube video. Make that a public comment. So here in the chat, you'll find the link to the PowerPoint under, I believe it's under bullet point number 7. I'll give people a chance to do that. But I'm going to be sharing the screen, so you don't necessarily even need the PowerPoint to follow along. But I thought it would be fun for us to talk over something while we're discussing this monumental discovery, potential discovery, I should say. And we'll couch that in the appropriate gravitas as we go on. So here is as a slide. I'm going to start off with a history behind this, how I came to set this meeting up with Sean. And that was because I saw an abstract for a paper entitled Limits on New Extraction of Cosmic Birefringence from the Planck 2018 Polarization Data. And then this may not sound as stupendously important and full of intrigue as both Sean and I found it. But the key sentence is shown here where it says that this beta, which we'll talk about what that means, is an angle that the authors, Miramori and Ichiro Komatsu, discovered had a value which is inconsistent with 0. So it says beta equals 0 is excluded at 99.2% confidence limit. That's what CL stands for. So they've increased the precision on this, and they've improved the accuracy too. And maybe we'll talk about the distinction between those two. Now, today, if you go to this link, you can download the PowerPoint. The links are all clickable. If you click on this link, you'll find abstract not found, which is kind of unusual for such a thing to happen. I'm not sure what it means or why that did take place, but nevertheless, it is no longer available. So you'll have to take my word for it. I do have a screenshot of the original abstract, which is saved for posterity. I can share that later on if people are interested. But really, this made me want to talk to Sean because it is the anniversary of something very important to us. So on the third slide, I've got a picture that shows Galileo on the left, and also wishing a happy 30th birthday to Carroll, Field, and Jackiw. I think that's how you say it, right, Sean? Jackiw?
Hmm.
And this is on a paper that Sean wrote while he was at the Harvard Smithsonian Center for Astrophysics. That's where you got your PhD, right?
That's right. This was my first ever refereed publication.
And it is enjoying its 30th anniversary. And not only that, it is enjoying a bountiful harvest of the currency in which scientists like Sean and myself traffic, which is citations. How many citations does this now have? You received over 1,000. I don't know exactly how many it has as of today.
I really have no idea, but it is over 1,000. I only know it's over 1,000 because Inspired tweets out when a paper gets over 1,000 citations. So I hadn't been keeping track until then.
I think behind you, I don't know if that's true, because behind you I see a hit counter, a citation counter in the laboratory. It's real time updating. Wow, that's amazing. Good. I got to get one of those for my 100 citations that I have. So getting back to the paper, the interesting thing that to me, I can't notice the date without thinking about Galileo, because you published this on Galileo's 426th anniversary, and that's very fitting because Galileo was one of the first people to talk about the concept of relativity. I believe he might have been the first, right, Sean?
We certainly attribute it to him. I'm always a little careful when we talk about historical things because my knowledge of history is not exactly very good, and physicists certainly don't worry too much about getting the history right sometimes.
That's right. But as you encouraged me when I was writing my book, Losing the Nobel Prize, we'll get a picture of that, de rigueur. So I've arrayed here, you can't see this, Sean, but on my couch in my office, I have 4 books that you've provided your encomium for, including my book, Losing the Nobel Prize, Leonard Mlodino's, your colleague up at Caltech, Stephen Hawking's Memoir of Friendship in Physics, and the Cosmic Revolutionary's Handbook. These are books that I'm reading for upcoming podcasts. So Sean is prolific at writing his own books, writing scientific papers, and also writing blurbs, which is just, he's a quadruple threat or triple threat, whatever we got up to. But getting back to this paper, when this paper came out, it's kind of been a slow boil. I actually do have a list of kind of how often these things have been cited. But I want to take us through the title. So it's not as attractive a title as Something Deeply Hidden or The Big Picture. How'd you come up with the title? I always judge papers first and foremost by their title and their abstract.
Like I said, this is my first ever published referee publication. So I was not the intellectual leader, really, of this effort. I did a lot of graduate student grunt work, and I did my best to provide the ideas that I could. The title might have been mine. Like I do often become the person who ends up with the titles. But this paper itself, there's a long version and a short version. I'll tell you the short version of how this paper came to be, because I was a new grad student at Harvard in the astronomy department. I'm not an astronomer. No one thinks I'm an astronomer. Like, what was I doing in the astronomy department? Well, the answer is the physics department didn't let me in, and the astronomy department did. And so George Field was randomly assigned to me as an advisor, and George was a world-famous theorist of the interstellar and intergalactic medium, so something I have literally no interest in at all. But he had sort of spent a long time as the founding director of the Harvard Smithsonian Center for Astrophysics. And then he left that position and sort of was intellectually curious, looking for new things to do. So he got into particle physics and field theory. And he actually attended a summer school as a student, at age 60-something. He attended as a young particle physicist. And Roman Jackiw was there giving lectures. And Roman at the time was very interested in electromagnetism in 3 dimensions. That's 3 dimensions of space, right? 2 dimensions of space. Sorry, 3 dimensions of space-time. So 2 dimensions of space, 1 dimension of time. And he gave these lectures on them, and that is the context in which this idea of chern-simons theory arises, named in part after our buddy, Jim Simons. And George, bless his heart, as the down-to-earth astrophysicist, he's like, well, okay, but what about 4-dimensional space-time? Like, what about where we live? Like, we don't live in 3-dimensional space-time. What is the point of all that? And Roman was like, well, you can't do it in 4-dimensional space-time. It would violate Lorentz invariance. So George's answer was, okay, let's do that. And that's when they brought me in, and we looked for, if we were to do this. And the reason why this paper has so many citations is because at the time, in 1989, 1990, the idea of violating Lorentz invariance was just anathema. Like, we knew that Lorentz invariance was right, so what's the point? But that's not a very scientific attitude. You know, the good scientist will say, well, if it's not right, how would we know? And this particular idea that we came up with was sort of the easiest and best way for Lorentz invariance to be wrong. There's some vector field that picks out a preferred reference frame in space-time, and it's gauge invariant, but it's also detectable experimentally. And so that's what we said. You know, we said, look, if Lorentz invariance were not true, here's a benign, innocent way to violate it, and here's how you would look for it. Here are the experimental tests you can do.
And so let's take us through it, maybe take a step back. What does it mean to be gauge invariant? What does it mean to be Lorentz invariant? What do those terms mean for those of us who may not be as expertly conversant in it as you?
No, exactly. So modern physics relies very heavily on the idea of symmetries, right? And a symmetry sounds like a big, sophisticated mathematical concept. All it means is there's something you can do, some transformation you can make, some change of perspective that doesn't change the underlying physical phenomena. So the most obvious thing is if I measure, you know, the strength of gravity right here, and I walk over 10 paces to the left, I measure the strength of gravity, I'm going to get the same number, right? If I measured the charge of the electron, it's going to be the same number. So that's invariance under translations through space. It doesn't matter where you do your experiment, and that's an example of a symmetry. Gauge invariance is another example of a symmetry that is specific to electromagnetism. It later got promoted to other nuclear forces, the strong nuclear force, the weak nuclear force, even gravity has a kind of gauge invariance. And it's more subtle than spatial translations because it's completely internal symmetry. It doesn't move you through space. It just takes the fields in your theory, the electromagnetic field, the electron, the proton, whatever, and changes them amongst themselves in a certain way. And it sounds all, like I said, very abstract and mathy, but it's absolutely at the heart of modern physics. All of these different symmetries highly constrain what you can do in terms of the laws of physics, what theories you can write down, what experiments you can do. So if anything, gauge invariance, which is at the heart of electromagnetism and so forth, is more sacred than Lorentz invariance. Lorentz invariance is, like you said, an outgrowth, sort of leveling up of Galileo's idea. Galileo said, it doesn't matter where you are, and also it doesn't matter how fast you're moving, right? If you're on a train and doing an experiment, you're going to get the same answer. Lorentz invariance is just the relativity version of that. You know, Einstein and Lorentz and Fitzgerald and Poincare, people like that 100 and some years ago, said it doesn't matter where you are and it doesn't matter how fast you're moving, but the way in which it matters is more complicated than you thought. So that's Lorentz invariance.
And when we speak about Lagrangian, I don't want to get too detailed, but when we talk about Lagrangians, that's sort of the underlying generator of all things of interest to physicists, is it not?
That's right. What you do as a working theoretical physicist these days is you either invent or find the predictions of different theories, right? Usually different quantum field theories, but maybe string theory or maybe some discrete theory, maybe different kinds of theories. So what does that mean, you have a theory? Well, it means you have some stuff, some fields, some particles, whatever, and you also have some equations of motion. You have some mathematical way of talking about how that stuff changes over time. And that's what the Lagrangian gives you. A Lagrangian is just a slick mathematical tool for generating the equations of motion for your stuff. So you say, when you propose a theory, here's the stuff, here's the Lagrangian. Any first-year graduate student can now go ahead and get all the equations of motion. I say that because I was a first-year graduate student when I did that with these equations. But that's the everyday life of a theoretical physicist these days, writing down Lagrangians and coming up with their consequences.
Now, did he end up being your PhD advisor?
He did, yes. Okay. I worked also with people from MIT, Alan Guth and Eddie Fari, but George and I wrote several papers together. We are still collaborating today, 30 years later.
Wow. So many people think that SS Chern was Jim Simons' PhD advisor, but they actually, if it had been the case, it wasn't. Jim Simons had a different advisor at Berkeley. He came to Berkeley to work with Chern as a graduate student, but when he showed up, he found out Chern was on sabbatical for a year and he had a different advisor. But as he talked about in my podcast with him a few months ago with Jim Simons, he said basically if he had shown up, he might not have ever created Chern-Simons theory, because he would have been just this rube of a grad student. And by the time he was actually working as almost a postdoc after only 2 or 3 years in graduate school, getting his PhD, he had the imprimatur of great success and great ability in mathematics that he wouldn't have had as a first year newbie graduate student. Right. So we can never live up to our graduate advisors' expectations. But yeah, go ahead.
Something I can mention is this idea of Chern-Simons theory, which is what we called it at the time. Obviously, Chern and Simons were pure mathematicians. They were doing topology. They were coming up with different, complicated to we mere mortals ways of characterizing 2- and 3-dimensional topologies. And so Roman Jackiw, who thinks of himself as a mathematical physicist, he was one of the people who really, starting in the 1970s, realized that you could make physical systems that are in effect 2-dimensional, right? Sheets of paper or sheets of conductors or something like that. So, and he knew enough about the math to know that there were things that could happen in 2-dimensional space that just can't happen in 3-dimensional space. So he borrowed this math idea from Chern and Simons into a physics idea. And then George and I and Roman turned it into a 3+1 dimensional physics idea. But by the time you get there, it's pretty far removed from what Chern and Simons actually did. And one of the questions I got at my PhD thesis defense was, do you think if you showed this to Jim Simons, he would recognize anything that you've done?
Yeah.
And at the time, I had to say, well, honestly, I don't know. I'm not completely sure. But now I know he would recognize it because of you.
Yeah, well, that's true. And he always is asking me, how's my Nobel Prize prospects looking? And we'll talk about that, because that, of course, drives some of the excitement, not the Nobel Prize, but the stakes that are involved. And another person I'm showing now, on the 4th slide, I think it is James Clerk Maxwell. Now, I wonder, if old James were alive and able to comprehend what he's seeing here, would he really understand the first set of equations? Lays this out really beautifully. You talk about gauge and Lorentz invariance are 2 symmetries of Maxwell's electrodynamics that have come to dominate all fundamental physical theory. And I wonder if he would have recognized that. I mean, as far as I know, he still had sort of, and again, sorry, apologies for getting back into history, but I can't resist these great scientists that we're talking about. You get into these different extensions of electromagnetism, but at its heart, it's really modifying this master equation, this Lagrangian, your equation 5, by the addition of this term. And the term has a very special force. Now, did this equation 6, where you add this 4 vector, did that just come to you out of the blue? I mean, what inspires you to, or your colleagues, you and your colleagues, to create such a thing that had never before been considered?
Well, again, yeah, so you want to start with some idea that in this case came from pure math, came from Chern and Simons. And they figured out a way to, they figured out what we now call a topological invariant of 3 manifolds. So what that means is you have some complicated mathematical thing which is 3-dimensional. So locally it has 3 dimensions. There's an up, down, left, right, forward, backward, but maybe it can wrap around itself, like there are donut holes and boundaries or whatever. And the ongoing program of mathematical topologists is to say, how do you know if 2 mathematical shapes are the same, if you can deform them into each other? And there's no algorithm for answering that question, right? So what you can do instead is say, well, here are 2 things I can calculate about these different spaces that would be the same if they were deformable into each other. So like the dimensionality of a space is a topological invariant, okay? And I encourage people to check out, I did a series of videos, The Biggest Ideas in the Universe, and I do a whole video on geometry and topology where I talk about this stuff. But anyway, their topological invariant was specific to 3 dimensions. It's not meant, in fact, odd number dimensions more generally. It's not meant to work in 4 dimensions. So our equation 6, no one else had ever written down before, even Chern and Simons. This was our 4-dimensional version of what something like a Chern-Simons term would look like. And the important thing about it, even if you don't know anything about Lagrangians or physics at all, if you zoom in and see the very first thing that appears there after the -1/2, there's a p alpha. and that P alpha represents a vector in space-time that picks out a preferred direction. That's why it violates Lorentz invariance, because Lorentz invariance says there are no preferred directions in space, there are no preferred velocities, etc. This picks out a preferred direction.
And that direction is the time axis, correct? Or the axis connecting?
We assumed it was, but you don't have to assume that. We made our lives easy. The paper was long enough and speculative enough as it was.
What's so interesting about this paper is that you actually not only propose a new modification to one of the most, if not the most sacrosanct fundamental theories of nature, namely Maxwellian electrodynamics, but you also subject it to test, observational tests. And we're going to get into that because obviously the subject today is the claimed extraction of this very effect, reproducing a type of special rotation in the cosmic microwave background polarization axis, linear polarization axis, that I want to discuss. But you know, the thing that really speaks to me is that you included not only the speculative theory, but also the potentiality for testing it with existing data that you had access to at that time. So I want to just get briefly into why these types of measurements are hard to do, and actually how we simple experimentalists go about trying to measure these things, and why. Of course, one of the main goals in cosmology is to detect perhaps the imprint of primordial gravitational waves produced by an expansionary period that we call inflation. And you've worked on this as well, and you've worked on an allied subject related to dark energy and accelerating universe. But I wonder, you know, if we comment on here, I'm showing a slide that I borrowed from Professor Matt Muse and the Cal State system. He has this beautiful diagram with kind of these blocks that my kids love to put together. Well, one likes to put it together and the other one breaks it, so it's kind of the symbiotic relationship. But he's declaring here there's a theory of everything that underpins all of reality, and it is supporting bricks that are labeled quantum mechanics, Lorentz symmetry, and curved space-time. Those then feed into the standard model of particle physics and general relativity. And then those support Newton's laws, classical dynamics, electromagnetism, atoms, classical cosmology, Newtonian gravity. But his point is that if you perturb the system on the next slide, you get something really wacky. That if you break Lorentz symmetry, you actually will have repercussions downstream. Namely, you'll be able to see effects in the atomic world, in electromagnetism, cosmology, and gravity. So the first thing I want to get into that some are asking in the chat room, what is your feeling about a theory of everything? Does such a thing have to exist? I've wondered often, I've never asked you this. I had a series of webinars over the summer with eminent physicists Lee Smolin, Sabine Hassenfelder, Eric Weinstein, Max Tegmark, Lisa Randall, and others. Do you think there's a need? Do we need a theory of everything, Sean?
Well, there is a theory of everything. The universe does something. Whatever the universe is doing, that's the theory of everything. The question is, can we human beings find a version of that theory of everything that we can understand and that covers all the bases? I think probably, but I don't know. We'll have to find out.
So one argument, you know, I haven't used this on you because we haven't spoken since December when we were actually in person in the travel district of Los Angeles International Airport. That was great. And yeah, we did a conversation on something deeply hidden. That was wonderful. You can find a link to it in my back catalog, and we also have links to your YouTube channel as well and to your books. But one of the things I've been asking lately is, in what sense do we talk about unifying gravity with quantum mechanics, but there's no, well, you don't believe in God, but there's no letter from, you know, some deity that says gravity and quantum mechanics have to be unified. And then I always hear, well, at the center of a black hole or at the Big Bang, there was a singularity, and you can't have a singularity without, you can't understand a singularity without a quantum theory of gravity. What if there are no singularities, first of all? Would you still say we need a theory of quantum gravity?
I mean, of course we need a theory of quantum gravity. It has nothing to do with singularities or black holes. Our current theory of gravity says if you have some energy or mass right here, it gives rise to a gravitational field of the following form. Quantum mechanics says I can take that energy or mass and put it in a superposition of being here and being there. Okay? So that superposition causes some kind of gravitational field. What kind of gravitational field does it cause? We need a theory of quantum gravity to answer that.
And some are asking you to do something very dangerous. Dallas here, I'll put up his comment. He's asking you to comment on the theories of everything of past guests on the show, including Stephen Wolfram, Eric Weinstein, and Max Tegmark. Would you take that challenge? Could you comment on why is there this proliferation of...
But I don't really agree with. I encourage people to check out my podcast conversation with him on the Mindscape podcast. It's good to be ambitious, but it's better to be right. So most ambitious ideas, including even observational tests, like we're going to talk about later, are going to be wrong. You've got to be able to deal with that.
Yeah. So I have a guest coming up in a few weeks, Nima Arkani Hamed of the Institute for Advanced Studies, and he's famous for saying things like, it's very hard to break the standard model. I mean, it's very hard to do what I'm depicting here, or Matt Muse is depicting here. But let's talk about that more. So first of all, Lorentz invariance, I'm just summarizing what you said earlier, the symmetry under various translations, rotations, and boosts. It's implicitly assumed within special relativity and GR. It's basically a foundational aspect component of the standard model of particle physics and beyond. And so therefore breaking it would be quite revolutionary. Another thing that Carroll Jackiw field effect would manifest is in parity violation. Can you comment on what is parity violation? Who cares if it's violated? Can't we all just get along with two hands that don't fit in the same glove?
Well, parity is violated in particle physics, so it's not that surprising. And by the way, let me mention that even though Lorentz invariance is absolutely a pillar of modern physics, one of the reasons why our paper was popular is because we violate it in a very benign, innocent way. We violate it in a way that doesn't make everything else break. It's still local quantum field theory. It's still obeying the rules that we're all set up with. It just picks out a preferred reference frame in the universe, which is certainly interesting, but it's not like we have to start from scratch with quantum mechanics and space-time and all of that. Parity is a particular subset, in some sense, of Lorentz invariance, which says you can take a system that has some shape, right, some orientation, and you flip its orientation. So if you have a set of vectors that are perpendicular to each other, you can sort of flip them so the other way around. I can't do it with my hand. I go left hand. There you go. It's the difference between this and this, okay? Left-handed and right-handed. That is the actual difference. Sometimes people say it's as if you hold a mirror up to something. And if you think about particle physics, right? If you think about two particles bumping into each other and interacting and going off their own way, it's the most natural thing in the world to think that if you have an interaction that happens with a certain probability because of the rules of quantum mechanics, and all you do is ask about the same interaction but in a mirror, it should have the same probability. It should be completely invariant under that, right? And so it was big Nobel Prize winning stuff when in the 1960s, they showed that no, actually parity is not an exact symmetry of nature. The weak interactions of particle physics violate parity. Gravity and the strong interactions and electromagnetism all satisfy parity, but the weak interactions violate it.
Isn't it possible, though, that gravity could violate it in the sense that you added a term to the Einstein tensor that's not unlike your term, that you would get chiral gravitational waves that would, in theory, we could never test it maybe, but some, including Lee Smolin, Stefan Alexander, etc., have thought about, if there is a theory of everything, all the forces are unified, gravity has to, at some point in the history of the universe, have chirality of parity violation. What do you make of such conjectures like that?
So you said two things. One thing is, isn't it possible that? And the answer is always yes. Any respectable physicist will always say, yes, it's possible. We don't know what the fundamental theory of everything is, like you said. So sure, it's possible. But then you said, doesn't it have to be that gravity violates chirality? Whatever? No, it doesn't have to be like that. This is where we should be humble. We just don't know. That's why this kind of exploration is important, because we don't know ahead of time how these things work. We should hypothesize that maybe they work and then go look for their experimental effects.
So let's do a counterfactual Gedanken experiment to throw a lot of Scrabble words in there. So imagine that the weak nuclear force did obey parity, and just somebody told you that in 1989, right? You're a bushy-eyed, bright-eyed graduate student. There's no parity violation in nature at all, Sean. Would you still write this paper? In other words, does not the existence of parity violation in the weak sector suggest that there could, as again possible, arise a violation in a lecture week or in electromagnetism solo?
Yeah, no, absolutely. I mean, physicists are people too. And when you think about different hypothetical scenarios that we haven't tested yet, different people are going to give different credences to them. Some ideas they're going to think are very reasonable, very probable. This is a good thing. Let's go look for it. Other ideas, even though they're also speculative and we're not sure yet, they're going to say, I'm not even going to bother looking for that. So there's no question that, we discovered both that parity was violated, and then we discovered the time reversal symmetry was violated, another Nobel Prize winning effort. So by now we're used to these symmetries breaking just a little bit. And, like I said, Lorentz invariance and these sort of orientation flipping symmetries are not even as fundamental as gauge invariance is. So maybe we shouldn't be surprised if these symmetries are broken at a fundamental level. I mean, I'm absolutely a big believer that quantum gravity might very well give rise to violations of Lorentz invariance. Other people have investigated this idea, but it's one of the very, very few handles experimentally that we might have on quantum gravity, so we should take that super duper seriously.
And then of the there are three discrete symmetries in which you can invert a parameter, a binary parameter, plus and minus, and charge and parity left to right, and then in time. Is there an analog of this Carroll effect, et cetera, in terms of time reversal symmetry being violated as a subclass of Lorentz invariance violation?
Well, like you say, there are these three symmetries. There's parity, which is the mirror, time reversal, forward and backward in time, and there's charge conjugation, which basically takes matter and antimatter and flips them into each other. So we've detected violations of P and C and CP and T, and all these different things, but the combination CPT, where you take an experiment, hold it up in a mirror, run it backward in time, and flip all the particles to antiparticles, that seems to be like a good symmetry of nature. In fact, there's a theorem, the CPT theorem, which says that under very general assumptions, CPT has to be a symmetry of nature. True confession time, we didn't even realize when we wrote this paper in 1990 that our theory violates CPT, which it does. And the reason, so, this is an example of the diagrams you showed. Once you break something a little bit, there are downstream effects of other things breaking that depended on what you started with.
Mark Gihaldia, I think I'm mangling that name, max to maximum extent, he or she is asking, wouldn't the many worlds interpretation be a theory of everything?
It's a different kind of thing because we have a technical definition of what we mean by a theory of everything. A theory of everything is not just a theory of the whole universe. It's a complete theory of the whole universe at the fundamental microscopic level. So something like the many worlds formulation of quantum mechanics is a paradigm. It's a way of saying this is how quantum mechanics works. But it's not a specific theory, right? Quantum electromagnetism, the standard model of particle physics, a qubit in a quantum computer or something like that. These are specific physical models. All of them can be described within the many worlds interpretation of quantum mechanics. When physicists say that we're looking for a theory of everything, we want the specific model that describes the actual world down deep into its bones, and maybe or maybe not, that'll be part of the many worlds interpretation of quantum mechanics.
So I want to turn back to our slides now. There's a picture of chern-simons for those of you playing at home. Let me get that up here. So this is the term that you added that we spoke about earlier. So you've already nicely described how that is added. I want to point out that this is not the first time that such a claim has been made, even in the context of CMB results. We're going to talk about an earlier violation detection claim in the late 1990s, which got me extremely excited as a graduate student, that you actually played a role in debunking. And I want to get to why I believe that shows almost a heroic level of scientific integrity. I've spoken on Eric Weinstein's podcast about you specifically being illustrative of the way a good scientist works his or her best to avoid confirmation bias, and how some of the great scientists in history, from Galileo to Einstein, fell victim to it. So I always say it's too bad they could have had good careers. But I want to take us back to August 2009 when a claim was made of a 3 sigma detection of CPT violation using a chern-simons like violation, the exact same term that you included in 1990. So this was by Jia, Li, and Zhang. They're all friends of mine, and they were basically analyzing data from the BICEP, WMAP, and Boomerang CMB polarimeters, and using those data to construct a very high or relatively high confidence several sigma detection, 3 sigma, which is higher than the current paper under discussion that we're talking about. And as I always joke, one of my late colleagues used to say, at 3 sigma you can come and give a seminar. At 5 sigma, they'll pay for the seminar. And at 7 sigma, you can go to Stockholm, but sometimes those go away too, by the way. But looking at this paper, this really set me off on a campaign with one of my graduate students, John Kaufman, who is now a PhD out in Boston area. And we started looking at cosmic birefringence of the Carroll variety and how it be manifest. So the next slide shows cosmic birefringence with basically what does it mean to exhibit this effect. Assume nature has this added term in electromagnetic Lagrangian. You add a chern-simons term. It would mean that the vacuum is birefringent. It would mean that a photon of the left circular polarization state would travel slower or faster depending on the sign of this effect and the coupling. It would travel slower or faster such that when traversing cosmic distances, a rotation would accrue, and a measurable rotation. The signature of polarization, and this is how your polarized sunglasses work, is that for every 1 physical rotation of the polarizer, my face will get darker and brighter. For some, this is great fun when I'm fully extinguished. It'll get extinguished twice per physical rotation. And this is relying on the fact that when you when you select one polarization state and then you measure an orthogonal state, you have 0 photons transmitted. And so what we do with our CMB polarimeters is we build detectors that are intrinsically sensitive to one polarization state or the other. And we essentially do this modulation where we rotate the polarizers with respect to one another in order to see if the incoming light is polarized, and if so, how. Now, what the universe would exhibit if there were such a CP, this Lorentz and parity violating property, is that an initially polarized vertical photon would rotate and become slightly horizontal or rotated with respect to its original orientation state. That's how you would detect it. And it was claimed, as I said, back in 2009, based on BICEP 1 data. So the original BICEP data, half the subject of my book revolves around BICEP 1, the other half sort of BICEP 2, and why the stakes are so high when we do polarimetry. And now I'm showing a cover of the New York Times. This is from April 18th, 1997, and I'll show it on the screen here. Here we go. And it's a cover, and it shows what I always think is interesting is that the New York Times is time translation invariant as well. So some of the same people that were on the headlines in 1997, including Newt Gingrich up here and Benjamin Netanyahu over here, they're still in the news. And Pataki, you sometimes hear about him. Anyway, it's interesting, but that's not what I want to draw your attention to. Down here, it's a subhead. It's on the front page of the New York Times. It says, "This side up may apply to the universe after all." So I know that I remember where I was when I first saw this paper, and I want to get Sean to take us back to 1997. There's essentially a claim made using the properties of radio galaxies, which are distant astronomical objects known to have certain polarization properties. You are a freshly minted PhD, or you're a postdoc, or maybe you're a professor at Chicago.
Postdoc at ITP.
Yeah, so you're at the ITP, and you are coming across this paper, which basically seems to have detected the very effect that now they don't cite your paper in the book in the New York Times, but it's effectively a detection of what you predicted. How did you feel as a person. Tell me what that felt like, that satisfaction that you might have had, must have had. Tell us what it felt like, and then as a physicist, and what happened next.
So this is, part of what I did for that original 1990 paper was, what we were doing was looking at radio galaxies. So radio galaxies often have these long, elongated jets, right? There's a black hole at the center spewing off matter in some direction. And what happens is if the matter gets spewed off, it stretches magnetic fields along with it. And so these magnetic fields, you know where they're aligned. They're aligned along the jet. That's you can test this experimentally, but it's the most obvious guess also. And what that means is that electrons swirl around perpendicular to the magnetic field. They give off radiation that radio telescopes can detect. So if you know what a radio galaxy is and does, you predict with very, very high confidence that the polarization of light from the radio galaxy will be perpendicular to the jet, because that's what the electrons are doing. They're moving around perpendicular to where the jet is. And so what George basically realized, George Field, was that if you collected a bunch of radio galaxies with redshifts and polarizations, and you use what we call the position angle, where exactly the jet was on the sky, an eager young graduate student could type all that in. This, by the way, was the days when you had to photocopy papers and then type in the data. Okay, so that was me, and then make plots of whether or not it was true that in fact the polarization was perpendicular to the jet. And if we had this birefringence effect, it would all be rotated a little bit, and it would be rotated more the further apart, the further away from us you were. So we looked for that, and we found no, there was no observable effect. We put an upper limit. There was not very much rotation, if any, in the polarization. And then, 7 years later, the front page of the New York Times says someone has discovered it. Look, to be honest, my immediate response was, that's wrong. There was no time, I did not get any moment of satisfaction where I said, oh my goodness, they found something. And I'll tell you the reason why. It's because in the New York Times article, they mentioned that the researchers used 160 radio galaxies. And I remembered I typed in 160 radio galaxies. So they weren't using different data or better data than me. They were using the data that I had typed in. I didn't collect any of it. That was collected by real astronomers, not me. But I knew that our data didn't have any observable effect in it, so I knew that they were wrong. And I'll tell you why they're wrong. And I feel like, dancing on the grave a little bit, because they were so wrong. It's kind of funny almost. For some reason, they thought that the polarization of the radiation should be parallel to the radio galaxy, not perpendicular to it. And so the problem with that is, of course, polarization is only defined plus or minus 180 degrees, because the electric field goes up and down.
Right.
So it's not like it's defined this way or that way, right? 180 degrees gives you the same answer, right?
Right.
So how do you know if what the polarization is? You have to resolve it somehow. And what they did was they said, well, in one half of the sky, we'll assume the angle is between 0 and 180. And in the other half of the sky, we'll assume it's between 0 and minus 180. Now, you and I know that it's actually 90 all the time. So what they found was that in one half of the sky, it was rotated by 90 degrees, and the other half of the sky was rotated the other way by 90 degrees. But that's the same rotation. It's not any different. So they just made a conceptual error. It was not like they made an analysis mistake or anything like that. So George and I, actually, George emailed me, and he said, you should look at the New York Times. And I said, yeah. And then he emailed me again. He said, no, you really should look at it. And I did. And literally over the weekend, we wrote a paper saying, here's why it's wrong.
Yeah. Well, you have a lot more control, self-control, stoicism than I do. Yeah, I always thought after you explained it, so I'm showing your paper from 1997 with the histogram distribution under the slide that says radio galaxy polarization. It was kind of like, remember when you used to play chicken in high school, Sean? And you'd say, you go right and I'll go left. That usually doesn't work out so well. So anybody who plays chicken, make sure not to heed that particular convention. But again, since this is one of my undergraduates, Kelsey Lund, put this slide together, the next view graph has a display of of the number of publications mentioning cosmic birefringence. It starts with a lonely peak at 1990, and that's Sean's famous paper, and then it builds as a slow, I wish my stock portfolio looked like this, and it's really just gone up almost exponentially. And the reason is, I think the stakes in some sense couldn't be higher. I was joking, earlier, if God, in my case, gave me a piece of paper and said, on this piece of paper, write down which do you want to detect, primordial B modes from inflation or Lorentz invariant cosmic birefringence and chern-simons type of, I would definitely choose the latter, because I think many people assume that the former took place, and it's almost a foregone conclusion that something like inflation, if not inflation itself, took place.
I mean, I don't know how much you want to get into
Yeah.
it, but part of this resurgence was many of the astronomy buffs out there will recognize 1997 as the year before 1998. And in 1998, people discovered that the universe is accelerating due to something which we call dark energy. And, sometimes good things come out of mistakes. And so even though I think that the Nodland and Ralston paper was a mistake, it got me thinking, again, about cosmic birefringence and things like that. And in 1998, I realized that rather than violating Lorentz invariance with some vector that we just made up, you could ask, is there an effect that dark energy could have on the polarization of background photons? And it's the same effect. And so I wrote a paper explaining that if dark energy exists and is dynamical, is quintessence, you should expect to see some cosmological birefringence. And to my mind, that's a way better motivation than violating the Lorentz invariance.
Yeah, I think that's your quintessence in the rest of the world paper. Is that it?
Right.
Yeah. So moving on, there were many other detections that have come about since, or measurements of non-zero rotation angle, but most of those we attribute in this paper with John Kaufman that I've linked here. This is basically the misapplication of the way that systematic errors propagate from experiment to experiment, and really the lack thereof of an astronomical reference source for astronomical calibration of polarization angle. The reason it's so hard, and you and I have talked about this before, a rotation of your detector by a minuscule amount can introduce the same type of effect that would masquerade as a real rotation of the CMB photon's polarization state, leading you to misattribute a detection of cosmic birefringence. And so we work to great lengths to reduce this type of systematic error. The problem is the way to reduce a systematic error, this is for the real cognoscente, the birefringence and systematics, you can skip over that, but that a small rotation of your axis can be detrimental, and it can be much larger and induce a signal far, far larger than the cosmic signals that are sought. And so we started thinking about, well, how could you calibrate your instrument's polarization angle? And it turns out, whereas for most astronomical sources, even in the CMB measurement, what the Planck instrument did for its temperature calibration, or the WMAP satellites, beach ball behind me, is that they use, say, Jupiter. And Jupiter is a known black body. It has a known size, and a distance to the Earth, etc. And therefore, it's a very reliable absolute temperature calibration standard. But there is no what I call standard stick. There's no object that we know exactly what its orientation is. And so we cannot absolutely calibrate our polarization angles using this with the CMB as easily as we can calibrate the temperature response. So we go to great lengths to do this, and some of the different ways are shown here. But again, none of these are as standard a candle as is the measurement of CMB temperature anisotropy. So it's a great challenge to us, but again, the stakes are quite high. We've actually gone so far as to propose building a satellite. Brad Johnson at the University of Virginia has proposed a satellite that would orbit the Earth, not looking out at the CMB, but looking down at the Earth, spraying it with a calibration signal that we would use to measure our polarization angles against. So before we turn back to the paper and maybe just finish up with the most recent Planck analysis and what's come of it, I want to point out there are many experiments that are seeking to measure the cosmic microwave background's polarization, in particular looking for effects due to primordial perturbations, whether they be gravitational waves or even density perturbations, and using it as a probe of all the physics in the intervening universe, and perhaps earlier, prior to the epoch of decoupling. But some of them are shown here. I think I got a fairly exhaustive list. But the comments, I asked Ichiro Komatsu and to come on this podcast with us, but he wanted to wait until some of these experiments return data. I didn't have the heart to break it to him that many of these are not observing and won't be observing for many years due to
maybe he knew that.
maybe he did, but let's get back to the original claim, which is that this effect of this cosmic birefringence effect was measured with this extremely high level of confidence, 99.2% confidence. What does that mean when you hear such a number? How should we think about the interpretation? I mean, if I had a 99.2% chance of dying in a plane crash the next commercial airline I took, I would not get on that plane. What do you think about this type of confidence level? How do you interpret?
Yeah, to be very clear, just so no one misunderstands, I think this result is probably going to go away. I think it's probably wrong if I were to bet right now, despite them saying it's a 0.2% of it going away, right? And that's because, this confidence level, 99.8 or whatever it is, doesn't mean there's a 99.8% chance this is right. What it means is that if you did something like this over and over again many, many times, you should not get a signal this large except for 0.2% of the time, okay? So the signal should be smaller. But that fact hides a number of other facts. Number one, you're looking for lots of different things, right? So you're actually doing a lot of different things, and you're going to get unlikely things. Someone wins the lottery, even though it's unlikely that you're going to win the lottery. Number two, you get more excited when you see a result than when you just see exactly what you expected, so you're more likely to write a paper about it. Number three, as you've already indicated, there are systematic effects. So there are effects that are not exactly random numbers. There can be hidden effects that push all of your errors in the same direction, and that can trick you into seeing something. And number four, most importantly, this would be such a big deal that you should be super duper cautious about it, no matter what, okay? So I think that it's very interesting, very intriguing that they claim that there's some evidence here. The confidence level, even at 99.8, you want it to be way higher than that, just as a numerical fact. And also you want it to be verified by independent groups, not just by one telescope, because any one telescope can have a secret little mistake in it. Mm-hmm. So it's not something that's going to be cleared up in the next couple of weeks.
And so that's very good to hear that take from you. We have a question from Stuart Volkow, who's the producer of the Into the Impossible podcast. He's taking advantage of his proximity to me. Stuart's asking, what is Sean looking forward to that may come out of observations from the next generation instruments coming online, like Vera Rubin Observatory, obviously Simons Observatory? Are there other probes that could get at this effect? You mentioned 130 radio galaxies back in 1990. Well, how many are there now? Are there other ways to get at cosmic birefringence besides the CMB?
Yeah, well, in fact, the CMB was not even something we thought of. If you think about 1990, it's hard, some of your viewers, I'm sure, were not born in 1990.
It's pre-Kobe.
That makes me very sad, but it's probably true. We hadn't discovered the anisotropies in the cosmic microwave background in 1990. We knew that they were there, and we knew that we had satellites in the sky that were going to look for them and hopefully find them, but we hadn't, the whole thing had been under-theorized in some sense, I'm sure Jim Peebles knew all of it, but the community as a whole was not nearly as informed about the meaningfulness of CMB anisotropies as they could have been. And so when George and Roman and I did it, we used radio galaxies, and that was more than good enough to show that the effect is going to be small if it's there at all. When I wrote my paper about quintessence, there, unlike my paper with George and Roman, where we just made something up, no good reason for it to be there. You can make up whatever size effect you want, and we put an upper limit on it. With the quintessence stuff, there is a target. There's a natural size for that effect to be, and I was tickled to see it was smaller than the current limits, but big enough to potentially be observable. That's why I got very excited about that particular effect. But these days, we do, as you say, look at the CMB to do it. People soon figured out that was something you could do. It's a more subtle analysis because you have to There's not like it's not like a radio galaxy, which does look like a stick in the sky, right? The CMB is a more complicated beast. But also, if you want to know what else I'm interested in, we all know there's something called the Hubble tension. There's this purported disagreement between cosmological parameters as measured via the CMB with the Planck satellite, WMAP, etc., and the expansion rate of the universe as measured in our local neighborhood, the Hubble constant. Okay. One of the possible explanations, this tension between these different measurements is tricky because, unlike the acceleration of the universe that we discovered in 1998, there's no obvious explanation. There's no obvious theory that would easily fit this particular discrepancy. So you kind of have to bend over backwards a little bit and you worry about it. The joke that theorists say is that it's an experimental result that has not yet been confirmed by theory.
I think who said Eddington said never believe an experiment until it's confirmed by theory.
There you go. So, but nevertheless, there are theories. People write down theories. My friend and colleague Mark Kamiankowski had a theory, one of many theories to propose to get rid of the Hubble tension, which is dark energy, but not now. An early period of dark energy before recombination, before the microwave background was formed. And that could also be a kind of dark energy that gives rise to birefringence in the cosmic microwave background. So even if we see the birefringence there, it's not necessarily the quintessence that I was talking about. It could be something more exotic. And so I don't have a target to shoot for in future experiments so much as I have a biggish smorgasbord of things I want to understand better. Parity violation, tensor modes with gravitational waves, reconciling the Hubble tension, all these things are potential discovery vectors, and so we need to push forward on all of them.
Yeah, that brings up, kind of an allied point from an experimentalist point of view. In addition to the many flowers that will hopefully bloom, when we go to measure the primordial beam modes, we get limits on this type of birefringence for free. We get limits on things like axions, which I want to conclude our conversation, just getting your take on that. But the other thing that we get that we know exists are called primordial magnetic fields. In other words, we know that magnetic fields exist in all bound clusters of objects. There's a cluster that's 10 megaparsecs across. It has a magnetic field that's been measured. But we don't have yet a measurement at truly cosmological distances that are not gravitationally collapsed. And so the theory is that at some early time in the universe, there could have been a seed field, perhaps a relic of a phase transition, etc. But we have a lower limit, and we have upper limits. And so what we try to do as experimentalists is converge the upper limit to the lower limit and hopefully result in a detection. And so that I see as a low risk. I see looking for, if you were just building an experiment and your proposal was to look for cosmic birefringence only, that probably shouldn't be funded. But if you can get all this other cool stuff, the primordial perturbations from inflation, primordial magnetic fields, limits on evolution of dark energy, etc., I think it becomes very fruitful to pursue such things where you have guaranteed results in some sense. Similar with neutrino masses, and one of the comments is a question about dark matter, which I always say neutrinos are the only form of dark matter we know exists that have mass and actually don't interact other than weakly and gravitationally. So a person by the name of Outsmoked is asking, "Hi Sean, I wonder why isn't dark matter mentioned in the formation of supermassive black holes? If we know that dark matter warps space, bends space, wouldn't it end up in a black hole in the end? So does dark matter be part of a black hole?"
Well, it might very well have something to do with it, but there's a good reason why we think that ordinary matter, even though there's much less ordinary matter than dark matter, has an easier time forming black holes than dark matter does, namely that ordinary matter can stick together. So you get a bunch of ordinary matter, hydrogen atoms or whatever, and they run into each other and they stick. You make a shockwave or a pancake or a bunch of stars or a black hole or whatever, because ordinary matter dissipates, it gives off light and heat, it interacts electromagnetically, and so there's all these extra forces over and above gravity that allow ordinary matter to condense into very dense objects and eventually form black holes. Whereas dark matter, as we know this from the bullet cluster and other observations, you send two clouds of dark matter together, they just go right through each other. So there might be a lot of mass in them, but it's not high density mass. To squeeze the dark matter into a really tiny region of space is really, really hard. It just tends to go right through your fingers.
And another candidate for the dark matter, in some extent, is the axion. I wonder, can you say something about axions? It was a term coined by Frank Wilczek, who's an upcoming guest on the podcast, and for his new book coming out early next year. I wonder, can you say something about that, and how is it an allied, or is it an allied phenomena related to the Carroll field and Jackiw mechanism?
Yeah, the axion is a very promising dark matter candidate. It's becoming more and more promising every day, not because of anything that axions are doing, but because their biggest competitor are something called weakly interacting massive particles, which we put a lot of effort into detecting and haven't detected yet. Okay, we could have detected weakly interacting massive particles yet. We haven't. We haven't yet crossed the threshold where we've ruled them out by any means. But every time we could have detected it and we don't, their probability goes down and the probability of everything else goes up a little bit, right? So the axions are more popular now than they used to be. And like the quintessence that we talked about, the stuff that gives rise to birefringence, the axion is what we call a pseudo-scalar field. If you do this parity transformation, take the axion and hold it up to a mirror, it turns into opposite of what it was. In some sense, it's going to remain vague for this discussion, but it's actually mathematically very well defined. And what that means is axions interact with electromagnetism in exactly the same way as this quintessence field would interact. The difference is the quintessence field very, very slowly rolls down its potential so that over cosmological time, a photon builds up a polarization rotation that eventually we can observe, whereas an axion very rapidly oscillates back and forth. So there's no net effect whatsoever on the polarization. There's particle physics effects. You can try to actually shoot a magnetic field or shoot a photon through a magnetic field and have it turn into an axion, or vice versa, turn on a magnetic field, let axions go through it, and look for photons being produced. But so it's a family cousin, but not exactly the same effect.
Very good. I can't resist just asking you your thoughts on the recent awarding of the Nobel Prize to Sir Roger Penrose, to Andrea Ghez, and to Reinhard Genzel. What did you make of it? How do you react to it? It's sort of a unique prize in a sense, going to, especially the component that went to Sir Roger, and then the observation. And notice it didn't say for a black hole discovery, did it? So what was your reaction to that Nobel Prize?
I mean, I think it's good Nobel Prize because it's good science that is being rewarded. I don't really follow carefully enough what exactly the citation was or so forth, but we've all seen these movies that they made of stars zipping around to some very massive, very dark object at the center of our galaxy. And I think this is one of those things that crept up on us, right? You know, black holes have been understood since the 60s. We've had some evidence for them since the 70s. The evidence got a lot better when Ghez and Genzel did their observations near the center of the galaxy. The evidence got even better when LIGO found gravitational waves from black holes, but LIGO already won the Nobel Prize, okay, so that's in there. So I think what happened was, you know, there's sort of it wasn't like a big phase transition so much as a gradual creeping up to the point where people said, well, we have enough evidence to say that, yes, black holes really exist, and here are these people who have observed them, they win the Nobel Prize. And then someone in the back of the room can say something like, well, that's the experiment, what about the theoretical side of things? And someone says, well, I guess, you know, probably the best work theoretically on black holes was Hawking and Penrose back in the 1960s. And Hawking is no longer with us, Penrose still is. So that's a very deserving Nobel Prize, although I was surprised that he got it. I would not have picked that.
Yeah, it was interesting. I mean, I think he's done a lot. He also has his own alternative cosmological models, which are nothing short of controversial. But yeah, it was certainly gratifying to see the recognition of this wonderful award and just the excitement that it brings to astronomy, winning racking up all this attention and accolades. Well, Sean, we've come to the end of the hour. I want to thank you so much, and also refer people to your YouTube channel, which is easily accessed, your Preposterous Universe blog, your many books, one of which has been shown this whole time, Something Deeply Hidden, a phenomenal book. I have an interview with Sean about that from back in December 2019, BC, before COVID. And I want to thank you for everything you do, both personally, that you have helped me, the way that you provide a role model for physicists and how to react and act with integrity as a scientist, your outreach, your communication skills, and your ability to eat almost any type of hot sauce, no matter what the Scoville rating.
Never been invited on the hot ones. That's a future goal for me.
I'll see what I can do. All right, yeah. Sean, be well. Say hi to Jennifer for us, and we wish you the best, and hopefully we'll have you back when these results are confirmed, if not sooner.
I'll be too important. I won't come on your podcast anymore. But
well, that hot sauce.
I'll remember the days. All
Bye,
right.
Sean. Thank you very much. Bye, everybody. Thank you so much for joining us on the Into the Impossible podcast, the special Sean Carroll edition. You can find a few different things I've done with Sean in the past. Find his blog. Find him on Twitter. And you won't be disappointed. Especially thanks to the producer of the show, Stuart Volkow, for helping arrange it and putting it together. That's all for now. Stay tuned for more upcoming, interesting, exciting analysis and news and interviews in the coming weeks with, as I said, Frank Wilczek, Barry Barish, and many other scientists. And I do want to put a plug out for a live stream I'm going to be doing with Adam Rees, Wendy Friedman, Jan 11, and I'm forgetting who else. There's Professor Sarah Seeger of the MIT. We're doing a live stream to commemorate the 100th anniversary of the Great Debates in Astronomy, which took place in 1920, the famous Curtis-Shapley debate. That live stream will be on the evening of November 10th, and we will do it in conjunction with the Wyoming Stargazing Association, which is an organization that I'm involved with that has access to half-meter diameter sized telescopes. We'll be reviewing some of the Hubble Space Telescope's greatest hits, because it's also the Hubble Telescope's 30th anniversary, 30th birthday. These are just incredible milestones to reach, both in our understanding of the size, the scale, the scope of our universe, in the case of the Curtis-Shapley debate, and also in the context of the Hubble telescope celebrating its anniversary. So who better to share it with than a bunch of friends looking at telescopes live on the air in the evening of November 10th. So stay tuned. Please subscribe to this channel and subscribe to the podcast version, the Into the Impossible podcast on Apple iTunes or Google Play. Please leave ratings and so forth. That's how we get more attention, so we can get great guests like Sean on such short notice. It's really such a treat, and the many, many luminous intellects that we've had on. Just this past week, we had Emily Levesque, professor of astronomy at the University of Washington, and in the next couple of weeks, we're going to have this stellar, outstanding cast of characters. So please do subscribe to the Into the Impossible podcast, to this YouTube channel. Leave a like, leave a notification. I don't know if you can leave a notification. Anyway, this has been a blast for me. Thanks to Sean. Thanks to all of you out there for your awesome questions. And please subscribe to my newsletter so you'll be the first to know whenever I do a live stream like this. Signing off, I am your fearful host in this time of pandemic podcast, Professor Brian Keating, University of California, San Diego. Have an awesome weekend, everybody.